This is going to be the Chapter 12 lecture tutorial. Chapter 12 covers the physical properties of solutions. So we'll begin the chapter by discussing what a solution is and, of course, the components of a solution that include a solute and a solvent. A solute is present in smaller quantities, as you would have read in your PowerPoints, and a solvent is the component of a solution present in larger quantities, and added together they make up the solution. The reason why you must differentiate between the terms there is simply because when we start to look at concentration units here and we begin to make calculations based on solutions, then we need to ensure that we are looking at the proper numerators and proper denominators of our equations. And so there is a differentiation between solute here, solution there, and when we move down to our other concentration units, we're looking at possibilities of solvent versus solution. So very important to make note that you're looking at different quantities. For example, if you have 5 grams of a solute and 50 grams of a solvent, then you would be looking at a total solution mass of 55 grams. So you must make sure you differentiate between quantities of solutes, of solvents, and of course the total, which is a solution. If you don't, you will plug in the wrong number into the wrong area and of course get the wrong answer. So we want to make sure we avoid that. Now, you also saw in your PowerPoints that we have differences in concentration where we have saturated and supersaturated and unsaturated solutions, but that's just a qualitative analysis and doesn't really give us any kind of numerical value. Well, that's where these concentration units come into play. The first one, which is mass percentage. Remember, percentage is a fraction, so part, the solute is the part, the solution is the whole. Part divided by the whole, and to get the percentage is times 100. Since this is percentage by mass, of course we'll be using masses of solutes and solutions here. The next unit of concentration is the mole fraction. X is the symbol for mole fraction. Again, a fraction is part over the whole. So part is solute A, solute B, so on and so forth. So the one component basically divided by the moles of the entire solution, all components. And again, since this is mole fraction, we'll be dividing moles by one another. No multiplying here by 100 because we want to keep it in fractional form. Molarity is probably the only concentration unit that you're familiar with quite a lot, even though mass percent and mole fraction should have been covered in Chem 1. Molarity is defined as the moles of solute divided by liters of solution. So here again, part over the whole, and we're talking moles divided by liters, and of course we must follow this unit. Again, if you have grams, convert them to moles, and the denominator of your fraction, the bottom part, should always be in liters. Now, molality here, we'll correct this, is probably a unit that you're not familiar with. Molality is defined as moles of the solute, just like molarity was, and that is divided by kilograms of the solvent. So just the solvent, not the solution, and of course it is actually a mass unit, and that mass must be in kilograms. So it's specific for kilograms. No other mass unit is allowed. Here we must use liters of the whole solution. Here we must just use kgs of the solvent by itself. So those are our 4 concentration units, and they will be important later on because we'll be discussing colligative properties, and our colligative properties will contain one of those particular concentration units in their equations. So if you don't calculate the concentration correctly, that will also affect your colligative property calculations. Speaking of colligative properties, we need to discuss solubility first and foremost here. And solubility, of course, here is for water because we're discussing aqueous solutions. So we need to ensure that we are aware of what would be considered to be water soluble. So if you're not familiar with your solubility rules, there is a slide with the solubility rules in there in the electrolyte review PowerPoints that accompany this particular chapter in this week's section on the course website, and you're welcome to review that. Also located in there, of course, is the electrolyte review from Chem 1. So if you need a refresher course on what electrolytes are, also review that, because determining whether something is an electrolyte or a non-electrolyte is also going to affect your colligative property calculations, which is, of course, the next topic we're going to discuss. Very quickly, again, if a substance is water soluble, it will then dissociate typically, and that's, of course, if it's an electrolyte. If it does not dissociate and it is soluble, then it is a non-electrolyte. So if a substance dissociates, such as NaCl, when in a water solution, it will dissociate, of course, into its ions. And in this case, with NaCl, it dissociates into those two ions. And that, of course, is very important. Why is it important? Because, of course, it tells us we have two ions present because of this electrolyte, given by this equation. All right, well, we do have strong electrolytes and weak electrolytes, and the significance of that is not going to be discussed here. But again, if you do have an electrolyte and it dissociates, you need to count the number of ions. Those ions, of course, are what make it an electrolyte, because electrolytes are conductors of electricity. So let's move on to substances that may be water soluble, such as glucose, sugars, alcohols, biological substances typically, but do not dissociate. That means they are not electrolytes. Take a look here. Glucose begins as a solid. It will dissolve in water, forming an aqueous solution, but notice that it remains in molecular form. It has not dissociated into ions, so those if no ions or charges are present, no electricity is going to be conducted. So again, starts with 1 unit, ends with 1 unit, and so on and so forth. So the number of particles remains as 1, whereas the number of particles here for NaCl specifically was 2. That particle is going to be important in our discussion of colligative properties. So let's discuss colligative properties here, and they'll tell us a little something about our solutions and how they behave under different concentrations. Our 4 colligative properties you can see now on the screen, which are vapor pressure, boiling point, freezing point, and osmotic pressure. You should know what the colligative properties are and what happens to a pure solvent, such as water all by itself. What would happen to water's vapor pressure, or its boiling point, or its freezing point, or its osmotic pressure if you added a solute, meaning you increase its concentration? Well, vapor pressure gets lowered, boiling point gets elevated, and freezing point gets depressed. Osmotic pressure increases. Here are your equations for each of the colligative properties and what these symbols represent. Of course, X would be the concentration unit used to determine effect of a solute addition to a solvent on its vapor pressure. Boiling point and freezing point use the molality as its or their concentration unit, and for osmotic pressure we use capital M, or molarity. And again, what these symbols represent, as well as example problems, can be found in your PowerPoints. What this I value here represents, of course, and that's again discussed in those electrolyte PowerPoints, is what we call the Van 't Hoff factor. That is the number of ions or particles that are formed when your particular substance dissociates in a solution. So the I value for an electrolyte will always be 1, because we start off with 1, just like we did here with glucose, and we ended with 1 particle. The I value for NaCl would be 2, because we have 2 ions. If we were to dissociate to form 3 ions, of course, our I value would be 3, and so on and so forth. Very, very important to make note, again, in your PowerPoints, that you must know if it's an electrolyte or if it's a non-electrolyte. And even if it is a salt, a metal-non-metal combination, is it soluble? If it's not soluble, it won't dissociate. So you must make sure it's soluble and it is an electrolyte. Both of those factors must be taken into consideration, and once those factors are met, those conditions are met, then it will dissociate into a number of ions. Make sure you know the proper number of ions. Don't mistake those polyatomics because they could give you problems. Again, look for those examples in your PowerPoints.